So welcome back, everybody. Congratulations on having made it through the first test. A couple administrative things to start off with. Specifically on the first test, the goal is to hand it back on October 22nd, so 2 weeks from the day of the test. I will bring them to class, and you can rifle through and find out why you got the mark you did. Good luck, everyone. I hope it went well. How was it? I mean, any comments on the test? Was it horrifying? No? Was there shocking questions that you weren't expecting? Like, oh my God, I can't believe you asked me that. Okay.
Symbolizations were a little trickier than
Okay, the symbolizations seem tricky. Okay, good to know. Like, probably different people experienced it differently, like wherever your comfort level was with the different aspects. I feel like we didn't do enough work on the symbolization stuff. Like, we spent more time on derivations and less time on symbolization, so hopefully we will even that out a little bit as we get into this next section. Any other comments on the test? Yeah.
Just having some scratch paper for the derivations.
Scratch paper for derivations, yeah. We started ripping off extra sheets. So next time what I'll do is have like extra sheets that we can just staple on. And I'll bring a stapler. Also, next time we'll be in the exam center, which is a far nicer room to write in. You'll get like a whole desk to yourself kind of thing. It's much, much better. Yeah. Okay with that? Not okay with that, but you know, we got through it. Right. Exercise 5 is up. 5, it's a relatively mild exercise compared to what you've been doing so far. 5 symbolizations in predicate logic. If you looked at this and thought, I don't know how to do predicate logic, don't panic. That's what we're doing today. Due Saturday, October 20th at 4 p.m. We're going to continue on with doing these on Saturdays. Once again, it's still a trap, maybe less a trap this time than before. A quick comment on the scores people have been getting on the exercises. So a surprising number of people, like loads and loads of people get full marks on these exercises, but a surprising number of people to me are getting less than full marks. And I hope that's because you're busy people, you're prioritizing, maybe you're no crediting this class and you just aren't getting to it. If you're stuck on these exercises, go on the Quarkus. So far, there have been people asking questions about practically every question on every exercise, and they're giving answers. So if you're stuck, if you're utterly, completely stuck, go on Quarkus, look at the answer, and then type it in. Seriously, this is not, that will not be considered dishonest or cheating or anything like that. That's why we've got that Quarkus there. So these exercises are supposed to be low stakes, like accept help. Like if you're doing the logic lab, then the TA is sitting, or one of the people is sitting there helping you through this. So don't try to face this alone. And if you get stuck, first step is either go to the logic lab or go on Quarkus and see if the answer's already there. And if it's not there, ask, and somebody will help you. So don't feel like you have to, like if you get stuck on, there's 3 questions you can't solve, you don't have to just accept that you don't get those marks. Go get those marks. Somehow, go get those marks. Like this is not a plagiarism sort of situation where like if you accept help, that's academic dishonesty. Most other situations in your academic career, if you do that, that's cheating, but here this is not. For those exercises, that is not cheating, is not dishonest, that's kind of what I'm expecting you to do, okay? So get those marks. Don't not get those marks. Figure out some way to get them, okay? Okay. I mean, if you're busy and you're just got other priorities, that's a whole separate issue. But if it's just the fact that you're stuck on them, find a way to get those marks, and there's plenty of ways to get them. Yeah? Okay. Okay, so that was sentential logic. We finished sentential logic. I hope you enjoyed it. I hope that you didn't do that thing that students often do when you finish something that you immediately forget it. I hope you didn't do that, because all of the skills that we developed in sentential logic are going to be still present in predicate logic. So the kind of logic that we're going to start doing now requires all of the skills that you've been developing all semester so far. So that stuff is still very much on deck, and then we're going to add in some more layers now, because that stuff was too easy, right? We're just blasting through it. No, actually, we're adding a couple of layers, but you've got, in some sense, the hardest part of logic, right? You've got the idea of symbolization, you've got the idea of derivations, you've got the idea of these connectives. That stuff is difficult to acquire, and really we're just adding sort of like bits on top of that. So if you got this far and you're doing reasonably well, you're in good shape to deal with this stuff. I'm trying to be emotionally reassuring right now because it's going to look way more complicated. Okay, the formulas are about to get much longer and much fancier looking, but if you've been developing the skills from predicate logic, you'll be able to see through that. You'll be able to see how it's not that much more complicated than what we've been doing. This is an incremental step that we're taking. It's not a humongous leap. Okay? A number of people have come to my office hours and described what I would call math panic. You're the sort of person, somehow something in your life has traumatized you with respect to math, and you just lock up. You're just locking up. So be aware of that and try to like work with it, work on it, do some journaling or something. I don't know. This is like an emotional problem that people are having. So if you're having math panic, if you're the type of person who has math panic, you might feel it again when we do this, but I promise you, you can get through it. Okay? Okay. Okay, so far, we've been doing predicate logic. And a sentence like the cat is on the mat, this is as deep as we could get into that sentence. P. The cat is on the mat. There's nothing, unless, if you can see a way that we could have broken that up. So if I offered you this as a symbolization question, I think that's as deep as we could get into the cat is on the mat. It's a sentence, a proposition that can be true or false, and we just sort of use this as our chunk. So this is our smallest chunk so far. Now what we're going to do now is sort of increase our resolution. We're going to get smaller chunks. We're going to get deeper into the sentence. We're going to crack open the sentence. We're going to crack open P and start dealing with its parts. And the parts of this sentence are the following: a subject and a predicate. The cat is the subject of the sentence. The sentence is about the cat. And is on the mat is the predicate. It's the thing that we're saying about the subject. Huh? Okay, so now we've got two parts of this sentence that we can deal with, that we can work with. So we're getting deeper into the structure of these sentences. Okay? And we'll symbolize this as subjects get lowercase letters and predicates get uppercase letters. Right? So C for the cat and M for is on the mat. Yeah?
Lowercase for the entire alphabet, or just like
We'll hang on one sec. We'll talk about that. So, no, I mean, well, there's a distinction. There's a distinction. So, just to say this one more time, the subject is the thing that the sentence is about, the proposition is about, and the predicate is something being said about the subject. And the sentence is true if the subject has that predicate, right? So if the cat is on the mat, then that sentence is true, right? If the property or the predicate or the description applies to that object, then the sentence is true. Yeah? So far I'm just telling you things that you worked out by age 5 on your own. I'm just giving names to stuff that you already know. Okay. So here's something that we haven't so far been able to represent using predicate logic. So if I say, Anne can dance, Anne is fun, Anne plays hockey, we would have just had to call those P, Q, and R. Those sentences would be as unrelated in predicate or in sentential logic as any random sentences. Venus is a planet, my cat is cute, and Anne can dance. They're just unrelated, right? Completely not connected in any way. We can't see how those sentences, there's something, but nonetheless there's something similar about those sentences, right? They've all got the same subject. So now that we're in predicate logic, we can represent that. So A is the name for Anne is the subject, and D is can dance. So we say DA. A has the property D. Anne has the property of being able to dance. Anne is fun. F is the property of being fun. Anne has the property being fun. And Anne plays hockey. H is the property of playing hockey or being able to play hockey. So Anne has the property H. Now we can represent the common aspect of all these sentences, right? We can say they've all got the same subject. They're all about the same thing, the same object. Yeah? Okay. So by breaking the sentence into its parts, we've gained better resolution. We're able to say what's similar between sentences that we weren't able to identify similarities between before. You go the opposite way, of course. You can apply the same predicate to different objects. Carl went home, HC. Ari went home, HA. Denise went home, HD. Again, in our sentential logic, those would have been just utterly unrelated sentences with no logical connection between them whatsoever. Now we can see that actually there's at least half of the sentence is shared between them. It's the thing that's being attributed to all of these objects, property of going home. Okay? Okay. So we're going to distinguish a couple kinds of subject. Here's one kind of subject that a sentence can have, a specific thing. So we call these names. You have a name for specific things. My name is Corey. Corey picks out a specific thing, i.e. me. We're going to assume that each name inside a symbolization, that is, if you're doing a derivation or you're doing a symbolization of some sentences, we're going to assume that once you've introduced a name, it always refers to the same object. Right? So you don't just say, A can be whatever you want at any time. Within a symbolization, these names get locked onto one and only one object. And a name doesn't just refer to people. You can name lots of things. You can name places or things or abstract objects like the number 17. Okay? And to answer your question, we are going to reserve the letters from A to H for names. So A through H are always names for specific things. And the rest of the letters are going to have a different job, so it becomes not just arbitrary, but important to maintain this convention. Okay? Okay, so that's one kind of subject that a sentence could have, a thing, a specific thing. And for any subject, we're going to apply a predicate to it. Predicates get uppercase letters between A and O. Hey, this is why before we required sentence letters to go from P to Z, because we're going to use the letters from A to O for predicates rather than sentences. That's why we had that convention. And using these two things, now we've got a new definition of an atomic sentence. In predicate logic, an atomic sentence is a predicate applied to a subject. Yeah? Whereas before it was an atomic sentence was just P or Q or R. Now it's two parts, a predicate and a subject. So far, so good? Okay. Okay, but we don't always, when you're constructing a sentence, you don't always refer to a specific thing, do you? Sometimes you make general statements. So you say something like, there are prime numbers bigger than 100. True sentence, right? But have you named anything specific? No, you're just saying there exists some number such that it's prime and greater than 100. Or all cats are mammals. You haven't named any cat, right? You said this general sentence is not a specific sentence about a specific cat. It's about all cats. Yeah? There are no elephants in this room. Well, you didn't name a specific elephant when you said that, right? You're saying there does not exist an object such that it's an elephant and it's in this room. Right? Okay, so these are a different class of sentences. These are general sentences. Sentences that don't name specific objects. They range over all objects. And we're going to have to introduce sort of possibly the trickier bit of predicate logic is how we're going to deal with these things. We need to deal with these things with variables. So we're going to say variables get lowercase letters from I to Z. and we use variables to make general statements together with quantifiers. Let me show you what that looks like. Okay, do not panic. It's going to be okay. This will all be super familiar by the end of the semester. So we have two quantifiers in the system of logic. We've got the existential and the universal quantifier. The existential is this backwards E, and it says there exists some. That is, exists at least one or more than one. It's compatible with either there being just one of those things or there being lots. It's just saying there's more than zero. The universal quantifier is the upside down A, and it says for all. Okay. And yes, this is a relic of the symbols for these are a relic of when we used to use typesetting. So like books were produced by people having physical chunks of metal. And they're like, hey, what's an easy way to come up with a new symbol? I know. I'll turn a symbol that you already have upside down. That's why we have the upside down A and upside down E. Very much a product of its time. Okay, so how do we use these quantifiers? We use them like this. So these are what your sentences are going to look like in predicate logic. If M is the property of having mass, then the first sentence says, for all objects X, the upside down A is for all, and X is the variable. It says it's a name, it's a subject, but it's a general subject. It's a variable that ranges over all objects. So for all objects X, those objects have the property of having mass. For all X, for all objects, those objects have mass. Yeah?
Why is it that the variable is switched with the predicate? Like, why does the predicate no longer come first? Is there a purpose for that, or is it just...
There is no specific reason. English speakers find it counterintuitive because we have a subject-object-verb construction for our sentences, but not all languages do that. So for people with a different language as their first language, this will be completely obvious and intuitive. For English speakers, too bad. This is just the way that logic works, I guess. I don't know. Yeah, there's not a really good specific reason why the predicate comes first and then the subject, but that's how we're going to do it.
I was just asking why this one switches it, because now the predicate is after.
The predicate is after.
Because for all, like everything... Oh wait, no, I guess, no. Oh yeah, has mass.
Has mass. Mass is the property, and X is the subject of that property is being applied to. I see another question. Somebody else had a question? Yeah.
The symbolizations you have there, is that in formal or informal notation?
I believe that's formal, actually. I believe that's formal. I don't recall, to be honest. Yeah. Yeah.
The X inside bracket and outside bracket, do they have the same?
Yes. Yes. So next week, we'll get into how the X in a quantifier or the variable in a quantifier gets related to the things inside the brackets. But here we're saying for all X, and then whatever's in the bracket, that for all X applies to any X that appears inside that quantifier. Okay? Okay. You can also negate these things. So you can say, it's not the case that for all X, X has mass. It's not the case that everything has mass. That's true, right? There exists particles, their neutrinos have no mass. Last time I checked neutrinos, they thought neutrinos have no mass. Is that right? Okay. So in fact, it is not the case that everything has mass. So it's not the case that for all objects, those objects have mass. Similarly, you can negate the existential. You can say it's not the case that there exists something with mass. That one's false, right? There are things that have mass. Yeah? So the negation out front just flips the truth value of the whole sentence, just like it did with predicate logic, or with sentential logic. Okay? Okay. Now, I want to alert you to the fact that these two sentences, you might be tempted to think that they are the same. Those are not the same sentences. Those sentences make different claims about the world. The first one says it's not the case that everything has mass. It is not the case that for all things in the universe, those things have mass. The second thing says, for all things in the universe, it's not the case that they have mass. Right, so the first one of those is true because there are particles, there are massless particles, right? There are things that don't have any mass. But the second thing is false. It's saying, the second thing there is saying, for everything in the universe, it's false that it has mass. Okay? Okay. Yeah?
I'm not sure if for the first sentence,
Yeah.
even though there aren't any parentheses around the entire thing, it still applies. The negation still applies to the whole sentence.
That's right. That's right. The negation applies to the whole. So AX bracket MX is a sentence in our new system. So MX would have been a sentence. That's like an atomic sentence. That's just applying a predicate to an object. AX bracket MX is a quantified sentence. So it's a sentence that's saying something general about all things X. So that's a sentence. And then if you add a negation sign out front of that, that's also a sentence. And the negation sign applies to, as exactly like with sentential logic, that negation sign applies to everything, the largest unit that it attaches to. Sorry, the smallest unit, sorry. Yep. The second one says, for all objects X, for anything in the universe, we're going to call those things X, it's not the case that those things have mass. So say, any object you pick. So the variable stands in for all of the names for every object in the universe. So we can kind of plug in specific things into these quantifiers. If you say for all X, it's not the case that it has mass. You say, I'm an X, I'm Corey, my name's C, so MC would be Corey has mass, and not MC is Corey doesn't have mass. And then you can go around through the entire, what this is saying is you can go around to the entire universe of objects, and that sentence will be true of them. So the first one says you can't go around through the entire universe saying that they all have mass. There's going to be one that doesn't have mass, or more than one that doesn't have mass. The second one is saying that you can go through the entire universe of objects and say of each of them, it's false that they have mass. Yeah?
Would that second sentence be the same as the negated existential quantifier?
Very good. Yes. So that second sentence is saying something like the following. It's not the case that there exists something with mass. Yeah? Did I have a slide about that? Oh, I did. No. Oh, yeah, I did. So I didn't do exactly the version that you said. I'm flipping the first one, but these two sentences make the same claim. So you can translate between the quantifiers. And one or the other reading will probably feel more natural and reasonable to you, but you can always do this. You can say, look, it's not the case that for everything in the universe, it has mass. That's the first one. The second one says, there exists at least something such that it's not the case that it has mass. There's at least one thing that doesn't have mass. And those two sentences do say the same thing. Those are exactly the same claims. Okay? It's not the case, first one says, not the case that for all X, for every, it's not the case that you can go through the universe and look at every single specific object and say, that's an object, and therefore it has mass. The second one is saying there exists at least one thing. In the universe of all of the things, you'll be able to find at least one such that it's true that it doesn't have mass. One of the billions of neutrinos screaming through your body at this very second, for example. Okay? They don't scream as far as if they did, it would be easier to detect. But okay, and these two sentences say the same thing. For every object in the universe, the object has mass. And the second one says, there does not exist any object such that it doesn't have mass. Do you see how those are equivalent? The first one says, if you go through the universe of all of the objects, you've got object 1 and 2 and 3 and 4 and 5, you can go through the whole thing, and every time you pick up an object, it'll be true that it has mass. Now, the second one says, there does not exist, it's not the case that there exists any object such that it fails to have mass. So once again, you go through the whole universe of what this is claiming is, you go through the whole universe of objects, object 1, object 2, object 3, object 4, and anytime you pick one up, you're not going to be able to find one that fails to have mass, which is just the same as saying every time you pick up an object, it's got some mass. Okay? And when we get to derivations, there'll be a rule, quantifier negation, that lets you flip between these two. Okay. So far, so good. I mean, I don't expect you to be super comfortable with any of this just yet, but really all we're trying to do today is get the idea of predicates and subjects and quantifiers on the table. If we get that far, we're doing great. Okay. So far I've been showing you very simple quantified sentences, but you can have complex ones as well. So if square is a sentence, then for all x square is also a sentence. And there exists an x such that square is also a sentence. So you can have, if for all x, if x, then if. So this first sentence says, for all objects x, if x has the property f, then it has the property g. So if f is being fun, then g is being great. Everything that's fun is great. If something is fun, then it's great. Okay? You can have, there exists a y such that y has the property j and y has the property g. You can also mix, so there's nothing wrong with mixing our letters here. So for all x, if x has the property g, then I has the property f. That's fine. Yeah? Yeah?
Are you saying for all I there, or there exists I? Like there's no quantifier?
Neither. We're not saying there exists an I. We're not saying for all I. We're saying for all x, if x has the property g, then this totally separate sentence, fi is true. Yeah?
Is the square symbol supposed to stand in for the subject and predicate?
Yeah. The square symbol stands in for any sentence in our new system. So it could be this whole thing, or it could be just kx, or it could be just a name, attributing a property to a name, or anything like that. Yeah. So just like with sentential logic, x stands in for a sentence of whatever complexity, from the simplest to the most complex. Yeah? Yeah.
Does I represent a name?
In this case, no, I represents a variable. Wait.
Yeah.
A variable. What did I say?
It's variable.
Yeah. So I and z, yeah, so it's a variable. Yeah. Okay. Now here's another thing you can do with these. Again, like visually this is more complex than the things we've been dealing with, right? This looks like it's got way too many parts, but you can handle this. This is just like what you saw before. So for all x, if x, fx, then gx is a sentence, right? Back in sentential logic, we would have called that P. If that thing, then there does not exist a y such that y has the property j and y has the property g. So what's the major connective of that sentence? What's the main connective of that first sentence? The conditional, right? So that's just one sentence, conditional, another sentence. And you can do all of the rules of sentential logic on these things. So if you have for all x, if x, fx, then gx, then you can use that and and you have this sentence, you can use modus ponens to get there does not exist a y such that jy and gy. Okay? And if you had the negation of this, so if you had, for example, not there exists a y such that jy and gy, then you can modus tollens it. Right? So all of the same rules of sentential logic are still in play. Yeah? And on the second sentence, you can see there's no problem with mixing together quantified sentences and unquantified sentences. So the first one is quantified. It's got a quantifier out front. Quantified sentences come as units, but they can be combined with things that aren't quantified sentences. So for all x, if f, gx, then fi, or jk. That's fine. I'm not kidding. I mean that. Okay. Okay. And one more layer of complexity here. You can have multiple quantifiers out front of the sentence. So the first sentence says, for all of the x's and for all of the y's, if y has the property f, then g has the property x. What's that?
Can you repeat it?
Yeah. So the sentence says, for all of the x's and for all of the y's, if y has the property of f, then x has the property g. Yeah.
What's the difference between this one and if you just dropped it for all x?
Well,
Because the last time we saw when there's only like for all x's and then you have something for y, I as well.
yeah. Well, then you're not saying it about all x's. If you don't have the for all x out here, you're not saying that about for all x's. So you can use a variable without it applying to everything in the universe.
Again?
Okay, so if we didn't have for all x here, if we just had for all y, if y has the property f, then g has the property x, then what we'd be saying is, for everything in the universe, if that thing has the property y, then whatever x refers to has the property g. But that's not the same as saying that for anything in the universe, it has the property g. Okay. Hopefully this will become clearer as we get into this. So I just want to get you adapted to the syntax right now. Yeah.
What do the quantifiers have conjunction? What
Wha-
do for all x's and for all y's?
Why doesn't why? Yeah, I mean, that would make sense, wouldn't it? So, I don't know. I guess that's just the arbitrary convention of the thing. So you could invent a kind of logic where you put conjunctions between these things to indicate that what you mean is for all x and for all y, but we didn't. This is the way we write it. I think that's one of those, that's just the system we're in kind of questions. Yeah.
For all the previous slides, when the all symbol and the all for all say show up at the same time, who has priority with the main connective?
Well, in this case, these are, so are you asking about these ones or
No, the previous slides,
previous slides? Yeah.
the last line of the previous.
Yeah.
With the main connective, we have a for all and we have a all.
So in the first one there, the main connective is the conditional.
Yeah.
And in the second one, it's the disjunction.
So if we want the for all be the main connective, we need a bracket for the main.
That's right. That's right. So you could say, so he's asking, could we do the following and make the for all be the main? So the for all, by the way, is not a connective, but this is just, so this would all now be one big sentence. All right, this just says for all x, if this thing is true, then there exists a thing such that. Yeah? Okay. So this now is just one big complicated sentence. Whereas before, if we didn't have those brackets, this is now a conditional with one sentence as the antecedent and one as the consequent. Okay. Okay, so be prepared for that. And we'll talk much more about what these mean next week, okay? Yeah.
You threw it, like, on the third one there, you just threw a negation in front of one of those quantifiers. Is there something you have to do to make that still, like, a symbolization, or is it, you could just put a negation between, like, the existential y, all, z?
I believe you can just put a negation. So he's asking, so if I said this, would that be still okay? I believe that's okay. I believe that's okay.
And that only applies to the existential, not to the...
Let me get back to you on that.
If it's in brackets.
So if you put this in brackets, then it would be clear. But I don't actually remember, to be honest. I think I remember, but I'm like 80% confident, and that's not quite good enough.
If the negation was there and you had two of them, wouldn't it force you to...
Two of what?
Sorry, if you, as it was before, so if you had the... Yeah, if you go back. So you had the all and the everything. So if you put a negation there in the middle, wouldn't it force you to put a bracket to say which one you were negating, because you have two?
That's kind of my question.
Yeah. Let's come back to that. Can we come back to that? Okay. Okay, especially since we're running out of time here. So, the exercise for this week is some mild symbolization. Hopefully, if you just get the idea of the quantifiers, you'll be in pretty good shape. But there's at least one thing that you need to know about these symbolizations to solve them. So it's symbolizing all blanks are blank. All whatevers have this property. And we do that with the conditional. So we say all cows are mammals. They are. They're warm-blooded, they lactate, they have live babies, so they're mammals. We do that by symbolizing it as such. For all objects so you might think that the subject of that sentence, all cows are mammals, is cows. But in logic, we say that subject of that sentence is actually all objects in the universe. So here's the logical way of saying this. Logical in a very specific sense. For all things, for every object in the entire universe, if that object is a cow, then that object is a mammal. So you can go around the entire universe picking up every object and say, is this object a cow? No. The antecedent is false, and the conditional comes out as true, right? So it's true that if this object is a cow, then it's a mammal. Good. That's going to be trivially true for practically everything, except for when you get to the cows, and now you have to sort of check. You say, the antecedent is satisfied. This object is a cow. Now, is it also a mammal? And every time you do that, you're going to come out with yes. So this whole thing is true. So it's true that for all objects in the universe, if that object is a cow, then that object is a mammal. And that's just a really clunky way of saying all cows are mammals. Okay? Okay, so I propose now to do just a couple examples of symbolizations in Logic 2010, just to make sure we've got this kind of thing. So, notice the convention here. So F bracket 1 says F and then whatever's in the 1 has the property. So F is the property of being good. That 1 should seem slightly ominous to you. It is slightly ominous because we're going to get into 2-place predicates and 3-place predicates. So is taller than, you need 2 things, 2 objects. To say X is taller than Y, you need an X and a Y. Right? So that predicate applies to 2 things. That's after the second test, however. So this is 1-place predicate logic, where all of our properties just apply to 1 object. But if you wanted to symbolize taller than, you'd need a 2-place predicate, and then you say F bracket 1 bracket 2. So far, we're just at 1-place predicates. So that's why there's that bracket 1 there. Now, how would you symbolize everything is good, where is good is the property F? Yeah?
Everything, I guess it would be a universal quantifier.
It's a universal quantifier. Good. So that's the first step. So we'll say, click on this, and we say, so notice there's a new list of things to choose from here. And we've got universal generalization, univ-gen. Good.
And then is good, well, you have F there,
Yeah.
and so that would be F of X.
Fx. Very good. And remember that our atomic sentences are now 2 parts. They now have 2 parts. So Fx is an atomic. So we say atomic, write in Fx. Okay? Do I remember how to do this stuff? I do. Hooray. Okay. Is that clear? All right, let's do another one. Notice how far in we've gotten. Look how much stuff you know how to do now. Look at all this. You know how to do all of that. That's great. Whoa. Okay. Yeah.
For the fx earlier, do you have to put it in brackets or no?
Do you have to put what in brackets?
Like the fx earlier, does it have to be in brackets?
It does have to be in brackets. It does have to be in brackets. Yeah. So, yeah, it doesn't say that here, but yeah, when you're writing out brackets. Okay, something is good. A much more modest claim. You're not saying that everything is good. You're not going wild. You're just saying there exists at least one thing that's good. Hopefully you subscribe to that. Okay, now what kind of, so again, this is quantified. What kind of quantifier is it? Existential. We're going to go down to existential generalization. X to gen, and we're just right down to the atomic. There exists an X such that X has the property of being good. Hooray. And that was good, so it's true. All right, we'll do 2 more and then we'll be done. Okay, slightly more complicated. All sweets are good. Anytime you see all, that's going to be universal quantifier. Now, all sweets are good. Yeah. It's going to be a conditional. We just did this. This is where we say, if there's anything in the universe such that it is a sweet, then it has the property of being good. So, conditional, and the atomic is a sweet, HX. If it's a sweet, then it has the property GX. Wait, nope, FX. Why didn't they make G good? All right, doesn't matter. Yeah? Okay. One last, and then I'll let you go. So, among sweets, only chocolate is healthy. Now, are we saying this about, so now you have to start asking yourself questions. We didn't use an all, we didn't use an exists. You have to ask yourself questions like, is this about some specific sweet, or just a few of them, or is it about all of them? It's about all of them. So that makes this a universal generalization. We're saying, of all of the objects in the entire universe, Among sweets, only chocolates are healthy. So, we got 3 properties here. Being a sweet, being a chocolate, and being healthy. Okay, so we restrict ourselves to talking about only the sweets by putting sweets as the antecedent of a conditional, just like we did with cows and mammals, right? We're saying, of all of the objects in the universe, let's just talk about the cows and then see what follows from that. So we're doing the same thing here. So among sweets says, of all of the objects in the whole universe, if it's a sweet, okay, now, only chocolates are healthy. Yep. It's another conditional. And now, once again, those sentential logic skills that you hoped that you could forget about and just start something new have to come back. Only chocolates are healthy. So what comes after an only? The antecedent or the consequent? The consequent. I heard it whispered, so I'm happy with that. Okay, so the consequent is chocolates. Consequent is going to be, what's the chocolate? IX, which means the antecedent is healthy. That's an atomic. JX. Okay? So, take a look at that sentence. Make sure I got it right. Oh, I did. Good. Okay, so for all the objects in the whole universe, amongst the sweets, there are only sweets that are healthy if they're chocolate. So, if it's a sweet, then if it is healthy, then it's a chocolate. Yeah?
For your last example,
Yeah.
all sweets are good.
Yeah.
The symbolization was for all things x, hx, then fx, which I think translated to if it is a sweet, then it is good.
Yeah.
Would it make sense to say for all things x, if it is good, then it is a sweet?
That would be a very different claim. What you're claiming there is, of all the things in the universe that are good, all of them are sweets. Sunrises, the smile of a newborn baby, none of that's good. That's what you're saying with that sentence, right? So the antecedent restricts what you're saying, and in that case, what you'd be saying is, I'm talking about all of the good things, and all of the good things have the consequent. Okay, we are out of time, so take a look at these. If you can't solve them, go on Quarkus, and we will help you. Okay, thanks everyone.